Yeah, we'll finish this chapter today, so on Wednesday we'll be starting the respiratory system. So just an FYI there. Quick review, because it was a long weekend. We had looked at the acute impact of exercise on plasma volume. So that when we actually start the exercise session, we see that reduction in plasma volume, which actually means that we've got more density of oxygen within less blood. So in the short term, that helps out a little bit, particularly if you're doing aerobic work. We looked at the fact that there are decreases in plasma volume, particularly if you're working out somewhere where it's hot and humid. So 10 to 20% for aerobic exercise, and anywhere from no change to 20% for resistance type work. All right, and then the chronic changes, chronic effects of long-term aerobic training is that we see an increase in plasma volume of anywhere from 12 to 20%. So we're looking at endurance runners having much higher blood volume, they've got more plasma, they have more red blood cell count. It doesn't appear that resistance has that chronic effect, doesn't have that same adaptation. So the only change we see with resistance work is in the acute scenario. And then we had a quick look at this table. This is resting adaptations. Okay, so use this table. It's a good summary of the difference between endurance training and resistance training on the cardiovascular system. All right. I think we had gone through all that. We looked at increased cardiac output, we looked at increased oxygen delivery, and we had said that we don't get that adaptation with weight training, but we do see a stronger left ventricle because of the increase in pressure when we're doing resistance work. And so the left ventricle hypertrophies in response to that kind of training to allow to keep up cardiac output against these really high pressures in the aorta. Okay, so that's where we had got to. And then we were going to look at how do we get the blood into the muscle tissue. All right. So this is important. It's all very well having this oxygen floating around in the bloodstream, but we can't do anything with it there, right? We have to be able to move it from the bloodstream into the muscle tissue. So that's the first thing we're going to look at. And we've got a big long term here that can seem a bit overwhelming, but it really isn't, okay? So when we look at the changes to the system when we exercise, we want to look at how much oxygen left the bloodstream and entered the muscle tissue, all right? So they use a very fancy term for this, arterial venous oxygen difference, and we shorten that to AVO2 difference, okay? But all they're saying is, what's the difference in oxygen levels between the veins and the arteries? Okay, so we've got the arteries coming into the muscle tissue, capillaries wrapped around the muscle, and the veins leaving the muscle, taking the blood back to the heart. So what's the difference in oxygen levels there? And that tells me how much oxygen was transported into the muscle. All right. So in our example that we have here, all right, our individual has 20 milliliters blood, 20 milliliters of oxygen per 100 milliliters of blood, right? So we get to the capillary, and remember that this capillary is wrapped around muscle tissue, right? So then when we look at the vein is responsible for taking the blood away from the muscle tissue. It's going to have carbon dioxide in it, remember, because we're making carbon dioxide. If we're working aerobically, right, then we're making carbon dioxide as a byproduct of oxidative phosphorylation. So the blood in the vein is going to be higher in carbon dioxide, lower in oxygen. And we see here, let's take the 15 milliliters of oxygen per 100 milliliters of blood. That means if I've got 20 here, I've got 15 there, the math is not very difficult. Somewhere in the middle here, I lost 5 milliliters of oxygen. Okay? So, at rest, about 5 milliliters of oxygen is transported from the blood into the muscle tissue. When we look at the second situation, this same person is now working out at a high intensity. Okay, so they're going for a hard bike ride up a hill, or they're going to go for a long run, okay? And obviously their oxygen coming in isn't different within that day, okay? So our 20 is still there at the artery side of the muscle. But when we look at the vein side of the muscle, now we only see 5 instead of 15. So now, again, the math is not difficult. 20 minus 5 means I've lost 15 milliliters of oxygen between the artery and the vein. So as that capillary is wrapped around the muscle, 15 milliliters of oxygen left the bloodstream and was transported into the muscle tissue to make ATP. All right? So we see quite a dramatic difference between oxygen use at rest and oxygen use during exercise. All right? So that's just because when we're exercising that we're going to be needing all this extra oxygen to make ATP. Okay? And remember, even if I'm not working aerobically, that recovery phase, that epoch, still requires aerobic metabolism to undo all the upset that occurs physiologically during an anaerobic bout, right? So even if I'm doing an anaerobic exercise, I still need oxygen. Might not be 15 milliliters, it might be a bit lower than that, but I still need oxygen to help me recover, okay? Okay. So that oxygen delivery can be calculated using an equation. It's called the Fick equation because that was the doctor or the researcher that kind of came up with it. It's pretty old. Remember, oxygen delivery is the same thing as oxygen consumption. Oxygen consumption is VO2. All right, so when we're looking at this oxygen delivery to the muscle tissue, we're really talking about VO2, right? How much oxygen is being used at the cellular level when I'm working, okay? So we can calculate that 15 or more right? We can use that 15, to calculate VO2, right? So I've got blood flow, which we had an equation for earlier, Q, cardiac output, right? Cardiac output is responsible for making sure that oxygen is being delivered to the working tissues, right? So blood flow times AVO2 difference. So I can substitute VO2 for oxygen delivery, I can substitute Q for blood flow, and we've got the idea of AVO2 difference. Remember that Q can be calculated by heart rate times stroke volume, and so that's our thick equation. Now that principle can be applied locally, so not by us, because we're not in a lab doing that kind of work, but you can look at the VO2 of your calf muscle, for example, running on a treadmill, if you had that kind of equipment, right? When we're working with VO2 in a more applied situation, typically we're more concerned with the VO2 of the whole body, of the whole system, because that VO2 represents capacity for aerobic work. Right? So if I look, the reason that we want to understand the equation is that it gives me some information about what is happening when we see an increase in VO2 max, right, when we start training. So if I increase Q, VO2 max would go up, or VO2 would go up, right? So if I increase cardiac output, then I would increase VO2. If I increase AVO2 difference, I increase VO2. Both those things happen during exercise, right? So increasing Q and increasing the redistribution of the blood flow away from the tissues that don't need it at that time to the working muscle tissue, right? Then we have much more blood flow, much more carbohydrate, much more oxygen for those muscles to make ATP. So this redistribution idea is important because it's one of the major changes that we see occur. Okay, so along the top of this diagram, I don't know how well the lighting is on the Collaborate view for you. Hopefully you can see that along the top it's red and along the bottom it's blue. So it's unfortunate that they used red and blue, I think, but they're not representing arterial blood and venous blood, okay? So it would have been more helpful if they had used orange and green or something. The bottom line is the rest situation, all right? So at rest, we've said that Q is about 5 liters per minute. So when we look at the distribution, if you're sitting watching a film or studying or sleeping, right, you're at rest. 5 liters per minute of blood is leaving the heart. So when we look at that distribution, where is that blood going when we're at rest? So 20 to, I think it's 30, I can't see, 20 to 25, I've got my glasses on, I still can't read it, is going to your digestive system. So a quarter of your blood flow when you're at rest is going to help you digest food, absorb nutrients, okay? Remove waste product, right? About 4 to 5% is going to your heart to provide oxygen and carbohydrate, glucose to your heart muscle. Remember our right and left carotid arteries, right? I mean coronary arteries, sorry. Okay. 20% or so to your kidneys, up to 5% to your bones, about 5% to your brain, 5% to your skin, maybe 15-20% to your muscles, depending what position you're resting in. You know, if you're sitting at your computer on a stability ball, then you'll be using more muscles to your postural more oxygen and blood to your postural muscles than if you're lying down in bed reading a book, right? So that's about the split. Now when we look at what happens during exercise, now our Q can be 25 litres per minute, right? And only about 4 to 5% of that is going to your digestive system, which is why you don't want to eat a big heavy meal before you exercise, close to exercising, because there isn't enough blood flow to digest that food anymore. And so it's going to sit there making you feel heavy and uncomfortable, right? So 4 to 5% to the heart. Okay. So you that's weird, right? I had 4 to 5% to the heart when I was resting, and I still only had 4 to 5%. But remember, it's 5% of 25, not 5% of 5. So it's a big increase of blood flow to the cardiac muscle, right? 2 to 4% to your kidneys. So a big drop in blood flow to your kidneys. So one of the things you might notice if you go for a long run or a long hike is that you don't need to go for a pee as often as you do normally, right? Because the more aerobic work you're doing, the less urine your kidneys are producing, all right? And they're working on absorbing back some of the minerals and things to help your balance. Up to 1% to bones. Remember, it's 1% of a lot more blood. Same thing here with the brain. All right. So we've got to keep the blood flow to the brain stable. All right. It can't tolerate a decrease in blood flow, because then you would faint because the brain doesn't have enough oxygen. But it also can't tolerate a huge increase in blood flow because there's just no room up there, right? There's very little space between your brain and your cranium. So you don't want piles of blood going to the brain. So we get 15% at rest, and only 3 to 4% during exercise, but again, that percentage is what's key. That maintains the balance there. It stays pretty even, all right? Might see a tiny increase, but very, very little, okay? What else do we want to see? A lot more to the skin, because we want to cool it off, right? We want to keep our core temperature cool, so we have to divert a lot more of the blood flow to the skin to release heat. And then look what happens to the working muscles, right? Huge amount of that 25 litres per minute is going to the working muscle now. Okay? Up to 85%. So the central nervous system is capable of redirecting blood flow away from the areas that aren't vital. Remember that exercise is a stressor, right? So what we're looking at here, when we look at this situation, is the body's response to stress. So the same thing would happen if you were in a big argument with your partner, or you had a little ding in the car, right? Or you've got 3 exams on the same day, right? Exactly the same kind of thing happens to your body, all right? So we're looking at a stress response. So the central nervous system is going to redirect blood away from your stomach, because you don't need to be digesting food when you're running away from the tiger, right? You need to run or punch, whichever you choose, right? Okay, so that's how you want to look at this situation. It's not specific to exercise, but it's what happens because exercise is a stressor. Okay? So, how does the central nervous system achieve this then? So it has 2 ways of manipulating the blood flow. It can vasodilate, okay? So it can increase the radius of the blood vessels, and if you look back to what we talked about on Friday, if I increase the radius, I increase blood flow, right? So when we look at the skin and the muscles, that's what's happening. Those arteries that are taking blood to the working muscle and to the skin get dilated, right? The other mechanism it has is vasoconstriction. So it decreases the radius of the vessels that are taking blood to and from your stomach and your kidneys. Okay. So vasodilation is strongly governed by the sympathetic system and by the release of norepinephrine and epinephrine. Right? It's really clever how it does this, but it explains a lot of things about how you feel when you're stressed, I think. Okay. Then the third big change that we see that allows the cardiovascular system to do its job, right, is that we see this large increase in blood flow back to the heart during exercise, right? So it's called venous return, okay? When we're at rest, the veins act like a reservoir. They're quite stretchy, and about 65% of your total blood volume is sitting in these reservoirs in the veins, right? If we think about it logically, that makes sense. It's just that probably isn't immediately where we would go, right? If my Q goes from 5 to 25, where did that other 20 milliliters of blood suddenly come from? Right? 20 liters rather. Right? Where did that suddenly arrive? I mean, we didn't just suddenly make that additional blood volume, right? So it's all sitting in our nice stretchy veins, waiting for us to need it back to the heart. Okay? So if it's sitting in the veins where the blood pressure is quite low and the blood flow is quite slow there, then we've got to find a way of oomping it back to the heart when we need it. Right? So we've got 3 ways of the oomph. The first way is venoconstriction. So when we're in this exercise mode and a lot of our systems are being dominated by the sympathetic nervous system, the sympathetic stimulation causes a constriction of the veins. So as they constrict, it pushes the blood up towards the heart. Okay? That's effective in other tissues. It doesn't happen quite that way in muscle. It's a little bit different in the muscle. Okay? It's not quite enough stimulation because the muscle is being stimulated to do all this other stuff. There isn't enough stimulation to constrict the veins there. But we have another mechanism within the muscle, and that in the muscle, the veins have these one-way valves. So you get this kind of timed contraction occurring, right? And it's, if I'm running or biking, it's the thing about aerobic work is it's very rhythmical, right? So I'm doing the same kind of motion all the time. And so that rhythmical contraction pushes blood, as the muscle squeezes, it squeezes the vein and scoots the blood up the vein towards the heart. And the vein has this one-way valve so that as the muscle relaxes, the blood can't come back down again, right? It hits a valve. Very cool. Useful idea for flying, right? So when you fly, particularly if you do a long flight, your feet and your ankles get pretty swollen, right? And they're always telling you to kind of move around in your chair, right? To lift your heels up off the floor. On an international flight, they'll let you get up and walk around the plane, or at least the bit of the plane that you're allowed in, because they don't let you through the curtain into the posh bit, right? You have to walk up and down in the cattle area. And part of the reason for that is to try to move some of this liquid out, and particularly the blood, out from your ankles and your calves and back up towards the heart. Okay. And then the third mechanism that we have is the respiratory pump, which will make more sense once we've done the next chapter. So we get these massive changes in pressure within our chest when we're breathing, and those are exaggerated when we're exercising. And so there's this kind of change in pressure encourages blood back towards the heart, right? Expiration, the pressure goes up. Inspiration, the pressure goes down. And because we see an increase in the rate and the depth of breathing when we exercise, then that's enhanced. So, you can relate these graphs back to that resting adaptations table, but also they give you a summary of what happens between being a sedentary, untrained person and a trained, someone that regularly does aerobic work. Okay, so if you go for a 30-minute run every morning or a 30-minute power walk every morning, then you would see these adaptations to one extent or another. Okay, if you like graphs and they're meaningful to you, then I recommend you look at them, right? So, for example, this one here is stroke volume. Remember we said that we see increases in stroke volume up to somewhere between 40 and 50% for an untrained person, and then it plateaus. So if you look here, the green line is the untrained person, and the orange line is the aerobically active person, right? So see how much higher stroke volume is when I'm trained. Okay, this is cute. Somewhere in there there's heart rate. That one's heart rate, I think. Okay, so remember, heart rate is the other way around, right? My green line is my untrained person. My orange line is my trained person, because heart rate goes down at rest or at any submaximal exercise. Maximum doesn't change, right? I can't change the maximum workload that the heart can manage, but I can change how hard it has to work during any exercise or at rest. Okay? So here, as I said, if you like graphs and they help you understand the adaptations that we see in these variables, use the graphs. If they don't help you because you look at a graph and you go, blah! Right? Well, I don't know what that means. I don't know how to interpret it. Ignore the graphs. The graphs won't be on the exam. The graphs are a tool to help you understand the adaptations in the variables of interest. Right? If the graphs don't help, don't use them. Okay? And that is the end of that chapter. So, questions? Oops. Hi, gang. Questions on the cardiovascular system.
Kind of a lot, but you did a good job explaining it, so I don't have any questions right now.
Thank you. That's nice to hear. Sometimes I think I'm speaking Chinese, but I'm glad that I was making some sense. So think about the fact that we're starting a new chapter Wednesday, right? Check the syllabus, because I can't remember whether I gave us 2 lessons for the respiratory system. We don't see anywhere near the amount of adaptation in the respiratory system, so there's not adaptations per se to talk about, but there's how do we get the oxygen into the lungs, and then how do we get the oxygen around the body. There's that kind of stuff to talk about. So I can't remember if it's 2 classes or 3 classes, but it does mean that there's going to be an exam next week, right? So that next exam comes around very quickly, but it's only on these 2 chapters. So hopefully that helps a little bit. Okay?
Sounds good.
Okay, well, if you don't have, I have office hours this afternoon, so if you're thinking about it and you're like, wait, I don't remember what that meant, come talk to me or send me a question in the discussion board Q&A. Otherwise, I will see you on Wednesday. Okay?
Awesome, thank you.
Bye.